how can we prove that a function is continuous at a certain point? How can we do so? There's something called the three-step continuity test. And the first step is that you have to show that the function is defined at some point A. So f of A has to exist. It has to equal a certain value. The second step is to show that the limit as x approaches A of f of x exists. Now, how do we do that? How do we show that this limit exists? Well, you need to show that the left side limit, the limit as x approaches A from the left side, is indeed equal to the limit as x approaches A from the right side. Only under those conditions will the limit exist. Now, the third step is to show that the limit as x approaches A from either side of f of x is indeed equal to f of A. So that's the three-step continuity test. So let's go ahead and apply it with a certain example. So let's say that the function f of x is equal to the square root of x plus 2 when x is less than 2, and it's equal to x squared minus 2 when x is between 2 and 3, and it's equal to 2x plus, let's say, 5 when x is equal to or greater than 3. So go ahead and prove that the function is continuous or discontinuous at 2 and 3. So let's start with an x value of 2. So therefore, we need to use these two functions. So what is f of 2? To find f of 2, we need to use the second function because x is greater than or equal to 2. So that's going to be 2 squared minus 2, which is 4 minus 2, so that's equal to 2. So f of A is defined. That's step 1. Step 2, we need to show that the limit exists. So first, we need to find the value of the limit as x approaches 2 from the left side of f of x. So on the left side of 2, that's when x is less than 2. So we got to use this function. And so that's going to be the square root of 2 plus 2, which is the square root of 4, and that's equal to 2. So now we got to check the right side. The limit as x approaches 2 from the right. On the right side, x is greater than 2, so we're going to use this function, x squared minus 2. So that's 2 squared minus 2, which we know is 2. Now, because the left side and the right side are the same, that means that the limit indeed exists. So we could say that the limit as x approaches 2 from either side of f of x is equal to 2. Now notice that these two are the same. So now we can make the statement for step 3 that the limit as x approaches A or 2 of f of x is indeed equal to f of 2 because they both equal 2. So therefore, the function is continuous at x equals 2. Now let's move on to the next example. And that is at an x value of 3. So we need to use these two functions. So first, let's determine if it's defined at 3. So f of 3, x is equal to 3 in the third part of the function. So it's going to be 2 times 3 plus 5. 2 times 3 is 6, 6 plus 5 is 11. Now let's move on to step 2. Let's find the limit as x approaches 3 from the left side. So therefore, we need to use this function. 3 from the left is going to be less than 3. So it's 3 squared minus 2. 3 squared is 9. 9 minus 2 is 7. Now let's find as x approaches 3 from the right. So we have to use this expression. So it's going to be 2 times 3 plus 5, which is 6 plus 5, that's 11. Now notice that the left side and the right side of the limit doesn't match. So therefore, the limit as x approaches 3 of f of x does not exist. And if the limit does not exist, it is not continuous at x equals 3. So therefore, you could say it is discontinuous at x equals 3. Now, because these 2 points do not match, and we don't have a rational function, this type of discontinuity is known as a jump discontinuity. Now let's work on some more examples. Here's another problem that you could try. Let's say that f of x is equal to 2x plus 5 when x is less than negative 1, and is equal to x squared plus 2 when x is greater than negative 1, and then it's equal to 5 when x is equal to 1. Rather, negative 1. So there's only one x value that we need to be concerned about, and that x value is negative 1. So go ahead and determine if it's continuous or discontinuous at negative 1. And if it's discontinuous, determine the type of discontinuity. Use the 3-step continuity test to do so. So first, we need to determine if the function is defined at negative 1. So what is the value of f of negative 1? When x is exactly negative 1, what is y? Notice that y is 5 when x is negative 1. So f of negative 1 is 5. So therefore, f of a is defined. So we're finished with step 1. Now, step 2. We need to prove that the limit exists. So let's find the limit as x approaches negative 1 from the left side. So from the left side, x has to be less than less than negative 1. So this is going to be 2 times negative 1 plus 5. We need to use this function. So that's negative 2 plus 5, which is equal to 3. Now let's find the limit as x approaches negative 1 from the right side. So on the right of negative 1, we need to use x squared plus 2 because x is greater than negative 1. So that's going to be negative 1 squared plus 2, which is 1 plus 2, that's positive 3. Now because these two are the same, the limit exists. So the limit as x approaches negative 1 of f of x from either side is indeed equal to 3. So we're finished with step 2. Now let's focus on step 3. Does the limit as x approaches negative 1 of f of x, does it equal f of a? Notice that these two do not match. They're not the same. So in step 3, we can make the statement that the limit as x approaches negative 1 of f of x does not equal f of negative 1. So therefore, step 3 has failed, which means that it is discontinuous at negative 1, but the limit exists. So what type of discontinuity do we have in this case? If the limit exists, we have this situation. We have a hole, but the function is not defined at the hole. The limit has a y value of 3, but the function has a y value of 5. So what we have is a hole, basically a removable discontinuity. In the last example, the jump discontinuity was a non-removable discontinuity. So if step 2 fails, if these two values are different, typically it's a jump discontinuity. If those two values are the same, and if step 3 fails, then usually it's going to be a hole. The only time you get an infinite discontinuity is if these values equal infinity. So if you don't have an infinity value, it's not going to be an infinite discontinuity.